Okay, I'm excited to hear this. It sounds like a really cool topic. Phoebe Heretz is a returning student studying physics and astronomy at SUNY New Paltz. She is an undergraduate research assistant on a global team of protoplanetary disk researchers called JDISC, or DSHARP-MIRI, that is expecting their first James Webb telescope data in early 2023. Phoebe is a passionate science communicator who leads observatory nights on the SUNY New Paltz campus, runs planetarium shows, and more. She hopes to pursue a PhD in observational research astrophysics when she completes her degree at SUNY in 2024. Her first degree is in songwriting, and she still participates in the local Hudson Valley music scene. Okay, take it away, Phoebe.
Thank you so much, Alex. And thank you so much to the MHAA for having me. This is a very exciting opportunity. So tonight I'm going to talk about how JWST will revolutionize our understanding of planet formation. So I'll give us a broad overview of what I'll talk about. First, I'll introduce the telescope and its mission objectives. Then I'll dive into the science of spectroscopy, which is used for many different things in astronomy, but I'll talk specifically about how we use it to study the chemistry of the universe. And then I'll introduce the objects that we're studying, these planet-forming regions called protoplanetary disks. And then I'll introduce the broader research team that I'm working with called JDISC. And then I'll work us up to the nitty-gritty of some of the research that I've been doing and the work I've been doing with them. And then I'll end with what's coming up next. So first, what is JWST? It's the James Webb Space Telescope, but to the astronomy community, it's better known as JWST. It's sometimes known as Hubble's successor, which is correct in some cases, but not in others, which I'll get to in just a moment. And it's a collaboration across the world with NASA, the European Space Agency, and the Canadian Space Agency. Over 1,000 people across 17 countries helped build it. And notably, it took almost 30 years for it to finally launch, and it cost about $10 billion. But it was worth every penny because it fulfills some very crucial mission objectives to understand our universe. So its main mission objective is our cosmic origins. And our cosmic origins across these three facets, the first being the origin of our universe. It'll help us see the most distant galaxies we've ever been able to see towards the beginnings of our universe. It'll help us study star and planet origins, peer through the dust to see into star and planet forming regions. And it'll help us study the origins of life. So we're going to use JWST to study exoplanets and exoplanet atmospheres and potentially look for biosignatures. So I really like this image because it gives you, so first of all, these are some of the people that helped build JWST, and they built it to scale model on the lawn of Goddard Space Flight Center. And I forget how big it is sometimes, especially with its sun shield. It's like a whole tennis court. So I just like to show that for a sense of scale. So after those 25 odd years, JWST was finally ready to launch on Christmas Day, 2021 from French Guiana. It flew on an Ariane 5 rocket. And I really like this statistic. It took 344 consecutive steps to go right for a successful launch. And if one of those steps had gone wrong and there were some scary moments, we would not have an observatory functioning today. So after it launched, it traveled 1 million miles into a point that we call Lagrange 2, which is like a gravity well in Earth's orbit around the sun. And this is where JWST is observing for us, 1 million miles away. And another fact that I really love about the launch was that it was so fuel efficient that they extended its mission life from 5 to 10 years to over 20 years. And this is so exciting because this is essentially the best telescope we've put out there so far as humans. And so we're essentially going to get twice as much data from it. We're going to get twice as much knowledge about our universe from it. So back to this conversation about JWST being Hubble's successor. So there are some comparisons, like they're both space telescopes, but JWST is not a replacement for Hubble. Hubble is still in operation, and we still want it to be operating for at least another decade. And crucially, we want them to work together because they actually don't see the same things. But I think it gets confused sometimes because it's such a larger, it's a much larger telescope, which you can see here. So what does JWST see? So the Hubble Space Telescope, it sees essentially what our eyes see, how our eyes perceive the universe in the visible spectrum from Roy G. Biv, essentially. But JWST, it covers some of the red optical, but then it stretches into the infrared, and that is JWST's sweet spot. And so we use the infrared for some very crucial reasons, which I'll get to in just a moment, that fulfill its mission objectives. So the first being, the infrared is going to allow us to see back the farthest galaxies we've been able to see that are so far away, they've been redshifted out of the optical and into the infrared. And so I have an image here from Hubble of some candidates of these very redshifted galaxies. And JWST, it's been in operation, science operation since July, and it's already like blown it out of the water. I have a statistic here, this might be beat already, but there's a confirmed redshift galaxy of 13.2, which equates to 13.4 billion years that light took to get to us, which means that light left when the universe was only 330 million years old. So another reason why the infrared part of the spectrum is helpful is you can see on the left-hand side, we have an image of the pillars of creation in visible light with Hubble. And on the right-hand side, we have the same nebula with JWST. And in the visible, the dust around the star-forming regions is opaque. It's really hard to see through. But in the infrared, we can cut through, and you can see clearly how many more stars pop out in the JWST image. So this is crucial to study star and planet formation. And finally, I wanted to point out, tying into spectroscopy, the infrared is really helpful to study the chemistry in cooler environments like planet formation, and to study molecular chemistry, which is more prominent in cooler environments like this. Oh, I also wanted to mention that the infrared, we as humans experience as heat. All right, so now that I've introduced JWST and its mission, I'll dive into the science of spectroscopy, which is the science that we are utilizing the most. So spectroscopy is best explained with a prism. So you take an incoming source of light and you send it through a prism, or what we call diffraction grating, and it spits out a rainbow, which we call a spectrum. And what the spectrum is doing, it's splitting up the light source into all of its component wavelengths or colors. And what's so magical about this is each element or molecule in the universe has its own unique spectrum, or like a barcode. And this is caused by the very unique energies that each unique atom needs to jump up and down energy levels. So I have examples here of both types of spectrum that we study. The first being absorption spectrum. So an example of this, I'll get to in a moment actually, as well as emission. I'll give you an example of each of them. So I really like this example. It's an example of an emission spectrum. So you might remember from science class, you would take a tube of unheated gas, and then you would put a source of energy through it to heat it up and excite it. So on the left here, I have an example of hydrogen gas. And when it heats up, it glows pink. And then when you take a diffraction grating to it and you can see its emission spectrum, you can see the very strong red line and the strong blue lines. And you can kind of see too how those colors combine to form this pink color. And so we can take this concept from where we are in the lab, in the classroom, in this room, and we can take that across the universe, and the same thing is going on. So on the right-hand side here, I have an image of the Orion Nebula, invisible, and it glows the same pink if we had gigantic eyes. So, I know what I wanted to do. So the absorption spectrum, the absorption spectrum, conversely, the exoplanet atmosphere that JWST released back in July is a good example of an absorption spectrum. So those are caused by a very hot source. So in this case, it's the exoplanet's host star. That hot source then travels through a much cooler medium. In this case, it's the exoplanet's atmosphere, and it creates an absorption spectrum. So there are two ways to read the chemistry in the universe in different environments. All right, so now that I've introduced spectroscopy, let's get into protoplanetary disks, and these are the objects of interest for us. So when a star is forming, when it's in its infancy, it's a phase that we like to call protostar phase. It's still eating, it's still hungry, it's still collecting a lot of gas around it. And as it's collecting and feeding, it kind of creates this accretion disk of gas and dust around it. And this disk is what we call a protoplanetary disk. So the leading theory is that whatever this star doesn't eat once it reaches adulthood, or what we call hydrostatic equilibrium, whatever's left over will eventually make up the planets in that solar system. And so I pulled up this artist's interpretation of what a protoplanetary disk looks like. And it's from a paper where they actually, I think they found like a Jupiter type evolved planet in a disk. So I thought that was an interesting find. So now we actually have some true images of protoplanetary disks. On the left is one of my favorites. This was from JWST a few months ago. It's an image of a protostar at the very center, and you can see an edge on protoplanetary disk. And the disk is so opaque that the star then illuminates the top of the gas above and below it like an hourglass. But then if we look at a face-on view of a disk, you can image these disks in radio. So that's a much longer wavelength than infrared. And this catches the dust emission coming from these protoplanetary disks. So this is an image of dust emission taken with the ALMA telescopes in Chile. And I will mention this later, but intuitively, the leading theory is that these gaps that form are caused by forming planets. So why do we want to study the chemistry of protoplanetary disks? Well, we want to know what material is around when the planets form and where that material is, because the processes of how planets form is still not well understood. So a good analogy of this is our own solar system. The inner planets are rocky, Mercury, Venus, Earth, Mars, but then you reach this zone, the asteroid belt, and then beyond it, you get these gas giants. And it's because the chemistry and the temperature, there's a lot of different factors going on. So for example, in this case, we think that when the ice line of water happens around the asteroid belt, that is then what causes gas giants to form. So we want to study where within the disk chemistry is, how it evolves, what impacts it moving inwards or outwards, and then that will help us inform the types of planets that form and inform our own origins. Where did we come from? What causes habitable planets to be created? So before I get into this, I just want to mention briefly, how did I get here? I'm technically an undergraduate student. So I got involved with this research when I applied to RUs last winter. Those are research experiences for undergraduates. Most of them are funded by the NSF. And I got accepted by Dr. Colette Salick at Vassar College. And I worked with her and 2 other interns over the summer. And then once our term was over, she invited me to keep working with her, which was really cool. So I'm still involved in this team, but I just wanted to mention for any prospective students out there, this is how you can get involved with cool stuff like this. All right, so now I'll introduce the broader team of researchers that I'm working with. They're called the JDISC team, which I had the honor of naming over the summer. The JWST Disk Infrared Spectral Chemistry team, but they're part of so many projects that they have other names as well, including the DSHARP-MIRI team. And this is a global team of protoplanetary disk researchers. It's co-led by my advisor at Vassar, Dr. Colette Salick, as well as Dr. Klaus Pontoppidan at the Space Telescope Science Institute. And this team is utilizing 4 JWST programs in its first cycle this year. So now I'm going to get into some of their incredible background, previous work. So members of this team are responsible for these now iconic images of protoplanetary disks taken in radio at ALMA in Chile. And so the disks hadn't been observed like this before. And so what they found is in larger disks, features like rings or asymmetries like this, or spirals are common in disks, and that was not known before. And then in smaller ones tend to be more featureless. Another foundational study that this team worked on was with the Spitzer Space Telescope. And this is more of a predecessor to JWST than Hubble is. Spitzer is in the infrared, another space telescope, and it's now decommissioned and replaced by JWST. So this team, they studied the chemistry of these disks, and they found that chemistry was prominent in cooler type stars, which are these small M and K type stars here. And chemistry was not detected or hardly detected at all in hotter type stars. So these were the molecules that they were observing. These are organic molecules, also known as volatiles. And I do want to mention before I move on the types of stars that I highlighted here. This is what we call spectral types. So MKGFABO. These are all spectral types. This is how we catalog stars, with M being cool, small, dim. They also live the longest, all the way up to O. These are very hot, massive stars that die pretty quickly. So, okay, then I just want to mention, so they weren't sure if, I feel like we have a better understanding now that they weren't sure at the time if in these cooler type stars that it was easier to see chemistry or if it existed, whereas in the hotter type stars, it was just, there's too much radiation that molecules just fly apart. So now the team is utilizing JWST. So what is their motivation behind this? So as I mentioned previously, the reason why we study the chemistry of protoplanetary disks, we want to understand the processes behind planet formation and what material is around when planets are forming. But more specifically, this team is interested in how chemistry is radially distributed around the disk. So how far away, for example, is water from its star? Where is carbon in the disk? Are there any processes that impact chemistry from moving inward or outward, such as these rings, perhaps? Maybe these rings prevent crucial chemistry from moving inwards or outwards. So what will JWST provide for the team? So the telescope has four main, my gosh, why am I blanking on the word? Components on board. So MIRI is one of them. And we're going to utilize a specific part of MIRI in the mid-infrared. So we're going to get spectra from MIRI MRS. And these spectra are going to be much more sensitive than the previous Spitzer Space Telescope spectra, which I'll show you in a moment. And this resolution of these spectral lines is going to allow us to break blended lines apart to see individual lines. It's going to be sensitive enough to detect previously undetected chemicals, so we'll be able to see other stuff that we weren't able to see before. And then it'll allow us to see optically thin lines to better quantify how much chemistry is there. And this all helps the team study this radial distribution of chemistry. So as I said before, JWST has a much higher resolution than its predecessor Spitzer. And this is modeled data. So this isn't their data yet. They haven't received any as of today, but this is a model of what the MIRI data is going to look like. And this is an example of the type of spectra they would receive from Spitzer about 10 years ago. So you can see just these beautiful, how much more resolution there is. So it's very exciting. All right, so now I'll get into the work that I've been involved with. All right, so last summer, I attended the KNAC RU. It was also the Vassar College ERSI internship. Our advisor was Dr. Colette Salick, and these are my fellow researchers here, Douglas Cobb at Vassar College and Anna Dignan at RIT. This was us after we gave a talk at Wellesley, so we're clearly very happy. And our main mission was to build 2 data sets for the researchers. So the first one, we scoured all of the published literature about these targets and their host stars, and we built a data set of characteristics about them. So that's stuff like the star spectral type, how old the star is, how big the disk is in radius or mass, if that was known. And then the second one we actually took in that Spitzer Space Telescope data, that spectra, and we reanalyzed those fluxes, or we reanalyzed the spectra and calculated the line fluxes and uncertainties if they weren't known. And these were the chemicals of interest. And this is just an example of what we did for most of the summer, compiling data sets. All right, so then towards the end of the summer, once our data sets were nearing completion, Dr. Salek advised us to start mashing them together, to start analyzing them together to see if any trends, any relationships popped out between stellar and disk characteristics and the chemistry present. And so one compelling trend popped out immediately, and that was disks in multi-star systems have a higher percentage of chemistry present or detected than their single star counterparts. And so I pulled up a photo of Tatooine for an example of a multi-star system. So the sun is rare that it lives by itself in a single star system. Most stars in the universe have a 1 or 2 or 3 other stars living with them. So on another exoplanet, there are likely 2 or 3 stars in the sky. Anyways, so we were excited to see this, but there's a large caveat here, and that is our sample size is quite small. And this is causing these error bars, these black lines, to be quite large. And so for this to be a more compelling trend, these black lines should not overlap. So we need to add more disks to the sample, but it was a cool find that can be investigated further. And we were wondering if it could be the gravitational interactions in these multi-star systems that causes a more turbulent environment that then produces more chemistry, more molecules to form, or perhaps creates an environment that allows us to see through and see those molecules better. And so then, more in line with Dr. Salek's goals, she asked us to analyze if chemistry detections had any relationship with these subfeature types that I mentioned before. So for example, we have rings in the disks, we have spirals, and we have these asymmetrical features. And so this was our first run at the analysis, and you can see there's nothing too extraordinary, too compelling here yet, but this is just our first analysis. Or there could be no trends. That's also an okay answer. So once we ended the summer, I felt like we had just started mashing these very too rich data sets together. So my goals for the fall was to continue probing them for potential relationships. And I had 2 big questions. The first being, there was a lot of disks that had a lot of chemistry detections, and there were some disks that had none at all. So I wanted to see if there's any other reason that could be besides spectral type, which I mentioned earlier. And the following, are there any chemical ratio trends that have not been discovered? And in the interest of time, I'm going to talk about that latter one because the first one did not provide anything fruitful, as is science sometimes. So I probed chemical ratios. And what I mean by that is, for example, down here, we have hydrogen cyanide over water. So the brightness of hydrogen cyanide in this disk versus the brightness of water. And so why do we study ratios? Well, a big reason is that as stars get brighter, their lines get brighter. So it's compelling to compare it to something else within the disk for there to be a relationship. Otherwise, it's just this kind of everything gets brighter, and that's not very interesting. So another key reason why we study why we study ratios is that they act as tracers for other important molecules or atoms that we want to observe in these regions. And so again, here are our 6 molecules: organic molecules, volatiles, so key ingredients for life. So the first ratio that I looked at was the ratio of hydrogen cyanide over water, which I mentioned before. And I picked this one first because it has been published with findings that there is a relationship between the disk characteristics and this chemistry. For example, higher amounts of hydrogen cyanide correlate to larger disk masses, and similarly, higher concentrations of hydrogen cyanide correlate to larger disk radii. And so I'll just mention hydrogen cyanide is a good tracer of carbon in protoplanetary disks. And carbon is a molecule that this research team is interested in exploring further in the future. And water, conversely, is a tracer for oxygen. So I'll explain my result here. And essentially, science is hard, but what I ended up being able to do, I was able to corroborate the published finding, but I'll explain it a little bit better. So this is the published finding here down below. They found that water becomes less prominent as the radius of the disk grows. And I seem to have an opposing trend here, but it's because I flipped the ratio. So that's essentially all that happened. Once I figured out what had gone wrong, I was like, okay, thank God. But then I'll also explain here what we mean by true detections versus non-detections. So a true detection is, here, I'll go back to the Spitzer data. Okay, so a true detection is a line that's quite sharp, and it's sharper, it's at this ratio with its uncertainty that we agree upon. It's sharper than that, it beats its uncertainty, if I'm explaining that well. But then a non-detection is a line flux that has too much uncertainty going on, but we don't want to discredit it because we are working with Spitzer data. And so a non-detection that has a lot of uncertainty could easily be resolved by JWST, just like that. So we still want to include them in our analysis. All right, and then with that, I had the great pleasure to be able to take this to AAS last month. AAS is the largest astronomy conference in the world. There was thousands of astronomers all gathered in Seattle, presenting posters, giving talks. There was this incredibly epic exhibit hall that was like astronomy Disneyland. There was so much swag from everywhere, from like NASA, Space Telescope Science Institute, all the observatories all over the world. I was truly in heaven. I got to present a poster, as you can see I'm really nerding out. And then I got to meet Klaus Pontoppidan, who is the other co-lead on this team of researchers. He was my first customer at my poster, which was scary because it's his science also. But it was very cool to be able to talk to him about his perspective on the science, what he's excited about coming up. And just a little bit of a brag alert, he was the scientist that led the reduction team for JWST's first 5 images. So he was the person that first downloaded this deep field data and looked at it by himself because he couldn't tell anybody about it. So it was really cool to nerd out with him about that and ask him about that very cool experience. So this spring, I'm going to switch gears a little bit. Their first JWST data is impending. So I think they asked me to help them out with like a more helpful tool to use as soon as possible. So what I'm going to be doing is creating SED models of the disks. And so what an SED is we have wavelength. So you can think of that one of those first slides I had with Hubble Space Telescope, JWST, that had the whole spectrum of light. So that's like what's mirrored down here. Here is visible light, and here we have infrared light towards the farther end of the x-axis. And then on the y-axis, we have brightness, essentially. So the larger the peak, the brighter it is. And so what stars, if they were perfect stars with no other junk around them, a star would have this curved shape like this, what we call a black body curve. But a star with a disk around it, a star with a disk around it is going to have this trail of warm dust and gas emission into the infrared that is the disk. So all of our protoplanetary disks kind of have SEDs that look like this. So what I'm doing is I'm taking these kind of like black data points here, which are photometric observations across wavelengths from different observatories over time. We just have a collection of them now. So I'm going to pull in these photometric data points and run them through an SED model. And I hope it goes well. I've been struggling with Python and reformatting data and stuff, but I'm determined to get it working. So that is what I'm working on right now. And this is a tool that they can later adjust for the JWST data and for these disks in particular. And it's going to help them with that radial distribution analysis. All right, so what's coming up? They should know on Thursday when the first objects are being observed by JWST. The Space Telescope Science Institute releases the observing log every Thursday. And so we're hoping that this Thursday, because our window is closing, so it should be this Thursday that we'll get word when our first observations are. And I want to speak for them. I can only speak for myself, but I'm excited to see this data. But I'm sure the rest of these scientists are so excited because one of the papers I mentioned with that JWST versus Spitzer diagram, that was from over a decade ago, in 2010. So these scientists have been waiting a long time for this data. So I'm very excited for them. And then Dr. Salek did propose cycle 2 observations to help fill in our parameter space. One key parameter space gap that we have is, so we mostly have M and K type stars, but she's interested in filling in G and F type stars. And then I guess what's coming up for me, I did apply to RUs and internships again a few weeks ago. So I hope to get another summer experience. Hopefully try to nail down my very still broad range of interests. Interest in the formation of things. I've come to really love star and planet formation. I really love these disks. I know them by name now. But I'm also interested in other scales like galaxy formation and even how the universe got here. So I'm hoping that another summer experience will help me narrow that down because I would like to apply to PhD programs at the end of this year. All right, and with that, that is my talk. If you guys have any questions, I'd love to answer them.
You just just mentioned that you're interested in, oh,
That's right.
okay. You're interested in the formation of galaxies. And I've heard that James Webb has basically found like kind of paradoxical information that, that conflicts with what we thought was the earliest formation of galaxies. Can you elaborate on that? What did it find that we didn't expect?
I actually don't know,
Oh.
but I am surprised also that there were fully fledged formed galaxies that close after the universe formed, just a third of a billion years. It's pretty short in universe scales. So I was surprised by that, but I'm not quite sure about the finding that you heard about.
Yeah, just because I'm nearby.
Because you said that you know some of the protoplanetary discs by name, do you have a favorite protoplanetary disc?
Let's see. Also at JWST, they had a booth of like epic space clothes, and they had a shirt with all of these discs on them. So I must have it. Whenever I have $50 extra, I must have it. I think this one's my favorite. AS209, if I'm not mistaken. Because it's beautiful. Look at it. Look at those perfect rings. So face on.
While I'm here, so.
I have a question, if
How
I
is
may ask.
James Webb, how is it powered and how does it send back images to Earth?
Sure. So the fuel reserves that it has are used to keep it in Lagrange 2, that gravity well, but also to operate the telescope.
What power is it?
Pardon?
What power is it? Is it solar powered? Is it radioactive powered?
I don't know. It's a good question. I don't know if it's solar powered. I know it blocks a lot of the solar radiation. I should know this. Does anyone else know? I'm sure there's a lot of. Pardon? An onboard reactor. Very cool.
Was there a question on the web?
I have one.
Sure.
Somewhere between, as these accretion disks form, there's shedding of the angular momentum that ends up giving you these nice flat ring-shaped things, and then Jeans instability will kick in, and some of them will coalesce into bodies. Perhaps these asymmetries that you've seen on some of these rings might be a start of that. I'm wondering, has any of your professors or guidance been talking about that side of it, and whether you're seeing some emerging coalescence into protoplanetary blobs?
Protoplanetary blobs, is that what you said?
Blobs.
Blobs?
Blobs. Masses that are starting to coalesce into planets.
Yeah, so that's the leading theory, is that we're seeing the effects of planetesimal formation in these subfeatures, but that formation and process is not well understood. So that's, or like why spirals are created. We're not sure yet, or like what creates these asymmetries. So I'm sure I told Dr. Salick that you guys would be excited to have her back, so she knows that, and she could go more into depth about it than I could.
Okay, well,
I got one more question.
Sure.
When they first put up Hubble, there was some problems with the optics, and they set up a space shuttle to correct it. They put glasses on them. Were there any problems with the James Webb telescope when it first opened up?
Yes, yeah. And we can't fix JWST because it's too far away. It's 1 million miles away. So if it goes wrong, we can't fix it. So some things that occurred were micrometeoroid hits. So these are tiny, tiny specks of dust essentially, but they're traveling so fast that there's like bullets, And there was a fairly large one that hit one of the mirrors that they had to correct for. So it's not impacting observations, but that is one event that happened, and they now have to adjust observations to kind of avoid this stream of dust that they didn't anticipate was going to be there. And then this team, the MIRI MRS instrument, this team was impacted by that. They had to pause it for a few months. So we were supposed to get data back in the summer, but then this one component of JWST had to be paused for a few months. And that was because there was this grinding of the gears that was causing too much friction. And so I actually asked Klaus about it. And the answer I got was they just turned it around. They turned it the other way. They changed the gears the other way. So I wanted to know more specifically, but that's the answer I got. Sure.
First there's so we had Shantha has a question online.
All right. Yeah. Actually, it's not a technical question. My question more about in NASA. 30 years ago, we have like 20%, only 20% of the female employees, and after 30 years, we still have the same ratio. Would you be interested to work for NASA?
Sure. Okay. I can speak to this a little bit. This past weekend, my friend was in a play about the Harvard computers. At Harvard about 100 years ago, the women were hired to analyze the spectra that came from stars with magnifying glasses, but they weren't allowed to look through telescopes. So it was a very emotional play, and I was asked to do a talk back at the end about the science that they discovered and also about women in astronomy. So I just did a lot of research about this, and the incoming generation of astronomers has a pretty even gender distribution, and it's the most diverse generation as well. So things are changing.
Yeah.
But
So-
sure, I'd like to work at NASA.
So with the DSHARP image, what are the little white dots in all the corners? Does that represent something to do with the actual image?
That's a good question.
They seem to be
I
different.
don't
so
know.
Yeah, okay, that's fair.
Guessing maybe the actual size of the star.
Maybe.
That's at the
Center
core.
star or something like
Maybe like ellipticity or something.
that. Yeah, they're kind of different shapes and sizes.
Yeah.
Central.
Okay. We have 2 questions on that from Alex.
Whoops, okay.
Lily first.
This is a really big question that you may not have gotten to yet. What is it with our solar system? It is just not typical. It doesn't belong up there. And somehow, we're here. And we've used that, up until Hubble, we thought this was the model for the rest of the universe, and it clearly isn't. And what's with the solar system?
I don't know. That is a good question. But I was excited when I was learning about these objects. You can see the evolutionary stage that we went through in them, because we formed from the same thing, an accretion disk around our protostar, and whatever was left over, the 0.1%, formed us. So I thought that was cool to learn, like, this was us at one point. But
Are there questions on Zoom again?
Yes,
Alec, go ahead.
yeah. Great presentation, Phoebe. This is so fascinating. I have a comment first. I'm glad to hear Dr. Salick would like to come back to speak to us. If you could send me her contact information, that'd be awesome. And my questions are, what is your future with this research group? Are you going to be working with them until you graduate?
I hope so. I've been taking it semester by semester.
Okay.
But it's been awesome. It's been truly
Yeah, it
incredible
sounds
experience.
amazing. I wish that I had that opportunity when I was an undergrad. My other question was about the biomarkers. Are the markers just those molecules that you mentioned, the organic molecules?
No, so they're for the exoplanet atmospheres, they're looking for molecules that can't be formed under natural circumstances. So they found sulfur dioxide, I believe, and that's something that is caused by photochemistry. And so that was not a biosignature, but they're looking for unusual detections like that can't be formed under natural circumstances. So like an Earth analog life example would be methane.
Right. That'd be cool.
Yeah, that would be cool. A little scary too, but
Right, right. What do we do if we find bio? Okay, well, thank you very much.
So I have a question about your data analysis. It's very exciting that you'll be having new data very soon. When it's released, do you have to spend the equivalent of another summer analyzing it, or do you have an analysis pipeline all set up and you just turn the crank and out come your answers?
that's a good question. Well, luckily, there's a whole team of professionals that will be ready to go. So I think I'm not sure like when I'll see it. I'm building this like tool for them kind of with the SED fitter that they'll then take and run with. So I'm not really part of the analysis pipeline, but I'm just excited to see when it comes out, what it looks like. Like, I'm such a nerd that I I did see JWST data that somebody else got, these spectral data, not even like beautiful pictures of stars and galaxies. I saw this and I cried. So I'm very excited just to see it.
Were there other questions in the back here? Oh, one more here. Okay.
So you talked about how in multi-star systems, there's a greater richness of chemistry, or at least the trend appears that way.
Yes. very.
What do you say, what are like the ramifications of a greater richness in chemistry?
Oh, that's a good question. I guess more stuff can form. Like if it's just like radiated out gas that like can't really coalesce, then more stuff can form. That would be my not very scientific answer.
You mentioned the term SED, and when you were talking, I was trying to figure out what does that stand for?
Spectral energy distribution.
Okay, thanks.
Did I hear
Any other questions back here?
that?
Any other questions on Zoom? Further questions in the room? All right, wonderful. Absolutely outstanding. Thank you, Phoebe.
Thank you so much.
Look forward to calling you doctor next time.
Oh, thank you. It'll be like 10 more years, but that's okay.